Okay, cool. We're recording. Let's go. Ready, team? Okay. Let's go through some naming. I ran out of time yesterday and I didn't want to rush it. So I just want to go through that today. I'm just going to switch it because I am right-handed. And I'll do some other naming examples. So if you guys remember on when we started learning organic chemistry, one of the requirements is going to be just a box of trying to name and draw them. So do revise that naming and drawing. I know for the spec internal, you weren't required to name anything. You just had to draw it. So just be mindful that in organic, you will be required to name things. When it comes to our geometric isomers, you are going to start with whether or not it's a cis or a trans whenever you're doing your naming. So since this one has the alcohols on the same side, that is going to be cis. So the first thing in your name should be cis. Now I can see looking at here, we have an alcohol group and we have an alkene. Just a reminder, when we are naming the alkenes, it is an ENE ending. Since that is occupying the ending, the suffix section of our organic compound, that means that the alcohols need to go as a prefix this time instead of a suffix. So alcohols, you have two choices. You can do prefix, that is the hydroxyl, or you can do a suffix that is OL, ol. Now in this case, since we already have a suffix, which is the ene, we have to use this one, hydroxyl. Are we good with that so far? All right. Next thing as a reminder, we need to specify which carbons those alcohols are on. So in this case, doesn't matter how we number it. If we number it that way, 1, 2, or 1, 2, it's still only 2 carbons long, so it's 1, 2. And remember, we have to specify how many alcohols there are. So it's going to be dihydroxyl. We finish off our naming, since it's 2 carbons, it is F, ene, to indicate that we have a double bond. So cis 1,2 dihydroxyl ethene, if I was to name that. This one here, because they're on opposite sides, we have the exact same name. The only thing we change is instead of saying cis, we say trans. So this one is trans 1,2 dihydroxyl ethene. We good? All right. Ready for the last example? And then I'll give you one more just in case, because I don't want you guys to get confused and think things are methyls that aren't methyls. All right. This last one over here, does this have cis-trans isomers? No, because we can see that when I look at the carbon, this has 2 of the same thing. So if either carbon involved in the double bond has the same thing, it is out. So in this case, this would be 1, 1, because both of those are on carbon number 1. Dihydroxyl ethene. Now, I'm not specifying where that double bond is because that double bond can only be in one location. But I'll give you guys a few more examples just to make sure that we are okay with the naming of the alkenes as a refresher and how do we include cis-trans. Okay? All right. Let's say we had this. Right, if I was to name that, what would I name it? How many carbons are there? 4. So these guys aren't branches. That's why I specifically picked this out. So be mindful of that. They are drawn like they are branches because I'm trying to indicate where they are spatially, but these are part of the straight chain. Okay? So in this case, I would have 1, 2, 3, 4. So 4 is bute. I also need to specify where on the 4 carbons is the double bond, because it could be here between carbon number 1 and 2, or it can be between carbon number 2 and 3, or it can be 3 and 4. Now, if it was on 3 and 4, it then becomes being between 1 and 2. Do we see what I'm saying there? Yes? Okay, I see head nodding. Julia's kind of confused. All right, this is between carbon 1 and 2. That's between carbon 2 and 3. That's between 3 and 4. But if it was 3 and 4, then I would start counting from here and go 1, 2. Okay? So this is between carbon 2 and 3. I use the lower number whenever I'm talking about the alkenes. So but2ene is how I name that. And then again, we have to indicate is it cis or trans because this does have geometric isomers. The CH3s are on the same side, so this is cis. Okay? If I had the double bond between carbon 1 and 2, what am I doing? 1, 2. If I had my molecule like this, so this is an isomer of the one before, structural isomer. So do you see how in this case, this carbon here has two different both has hydrogen. This one has an ethyl chain and then it has a hydrogen. So this one meets the requirement, has two different things attached to it, but this one does not. So this has no cis-trans isomers. So when I go to name this, this would be but1ene. Because now between carbon 1 and 2. 1, 2, 3, 4. So that's how we name these bad boys. Cool. Questions, concerns, or comments? Nice little refresher to naming. Alrighty. Can I move it? Julia, can I move it? Okay. Cool. So let me talk about what we're doing today so that way we have no surprises. All right. So, yeah, or she's not over her cough yet. All right, so some things to keep in mind on what we're looking at today. I want us to just focus some more on geometric isomers. I decided to separate the geometric and the optical isomers from each other as questions, just because I think it flows better that way. So first thing is defining what they are, which we've already covered. The next thing I want us to think about is how are they made or used in chemical reactions. I made this really tiny, so I'm stuck. Can I zoom in? No. Okay, let me just make this bigger temporarily, so that way we can actually read it. Okay, so the stuff that we are covering today is going to be Markovnikov's rule and Zayt's rule. In level 2 chemistry, they do ask a specific question on Markovnikov and Zayt's rule where you have to explain why two different things form. In theory, it could come up again at a level 2 or on a level 3 exam because level 2 stuff is fair game for level 3, but I haven't seen it in ever before, I don't think. So just be mindful that the concepts from last year still apply to this year, but the focus is probably going to be the stuff that is for this year. The reason why I still want to cover Markovnikov and Zayt's rule is because it still comes up in a couple of questions indirectly. So it can come up on the structural isomer questions because sometimes they will mention like, oh, this structural isomer cannot form geometric isomers or it can form geometric isomers. So just be mindful that it can pop up in that question, which you guys have had exposure to before we started spec, and I will give you guys some more exposure to that probably this week. The other place it does come up is in the flow chart. So one of the questions you're going to get is a giant flow chart with some stuff filled in and some stuff not filled in, and every so often you do need to be able to figure out, okay, which isomer do I want from the geometric isomers? So it's really important that we still cover this material even though it is not directly asked anymore. So, I'm just going to undo that so it's nice and tiny again. So, before I cover that, I want to make sure we do some pre-learning because I think that's really important so that way you guys have some prior knowledge before I start giving you the information. So, these are the SciPad pages for Markovnikov's rule. Some of you guys have just the organic book, and some of you guys have the full external book, so I've noted both pages. So Markovnikov's rule, 129 to 130, or 17 to 18. Zayt's rule, 131 to 132, or 19 to 20. So do give that a go. If you forgot your SciPad today, I did put it onto Google Classroom as well, so if you need those pages. So give that a go, see what you guys can understand. I'm just mindful of time. How much time we got? Half an hour, 15, what is that, 45. Shall I give you 25 minutes? Because I want to make sure I have a decent amount of time to give you your notes. Okay? Try a bit of both. Don't try to complete all the Markovnikov's pages and all the Zayt's pages. I would rather you do a couple questions in each just so you can see how both of them work. All right, cool. That's us. All righty, team. So, cool. We are recording. Let's find what I want to find. So I just want to quickly go over Markovnikov and Zaytev's rule just so you guys know what you're doing with this case. And I'll give you guys some general notes on addition and elimination. So, something to keep in mind. Let me just find you guys some exemplar questions from No Brain Too Small. Just so you guys can see what I'm thinking about. Okay, organic compounds. Collated questions. I just want to show you guys the conversion reaction schemes so you guys are used to what that looks like. So, there's no surprises. You can understand where we're working towards. Let me just make this a little bigger. No, stop. Too many things. Where is the bigger? There it is. Okay. Whoa, too big. Okay. So, oh, that was a nasty question. Nasty question. All right. So, something I want you guys to keep in mind is that you are very likely to get something called a flowchart question. And we are basically talking about how do we get from one organic molecule to a different organic molecule looking at various chemical reactions. There are a couple different types of chemical reactions that will come into place. I'll write them down so you guys can have a list, and we'll talk about them as we're going. We're not going to talk about all of them today because I don't think that's ideal. I don't want to talk about them all today either. All right. So the types of reaction, now I'm trying to remember off the top of my head. And in fact, you talked about two today looking at the notes. So the first one that we have is addition, which sounds like what it sounds like. You are adding to the molecule. And in order to add to a molecule, the only way you can add to a molecule is that it only works if the molecule is unsaturated. So it has a double bond or a triple bond. Only works if the molecule is unsaturated. Gotta go? Okay. AKA is C double bond C or C triple bond C. All right? Because what that means is I can break the double or the triple bond and add to it. It doesn't work if I have a saturated molecule, so that means that all my carbons have single bonds because there's no way for me to add to something that already has 4 bonds. You can't have more than 4 things attached to your carbon. So that's what that is. The other one that we have seen today is elimination, which again sounds like what it's supposed to. You are removing things from the molecule. And this creates an alkene or an alkyne. Okay? So that's elimination, which again, you've seen in the examples. All right? There's a couple more. Do you guys want me to talk about them now or hold off? Now? Okay. Another one that you might see is substitution, which again sounds like what it should be doing. You are swapping out one functional group for another. Say, for example, I swap out a BR for an OH. That's substitution. Trying to think what else is there. Substitution, elimination, addition. Then there's oxidation and reduction. These two I'll show you when you guys actually get to the flow chart because it doesn't, it's a redox reaction is what that is. All right. Are we okay with that so far? All right. So based off of this little flow chart here, these have different types of reactions, and you're going to have specific type of reagents in order for those reactions to occur. Every so often, they do ask you to also identify the type of reaction, so do keep that in mind, that it's useful to know this is an addition reaction, this is an elimination reaction, etc., etc. Like I said, they're not going to ask you specifically about Markovnikov or Zeta's rule on the assessment, but it will pop out in things like this. So you see how it says product M does this reaction, and we only want the major product. So you need to know which is the major product. So that's why we review it. Okay? So let's talk about those two reactions. I'm just mindful of time. So the first type of reaction we have is Markovnikov's rule. Markovnikov is an example of an addition reaction. So we have taken a double bond and we have broken it and we've added to it. Addition. All right? Now, Markovnikov's rule only comes into place if you have two things. First off, you need an unsymmetrical, an unsymmetrical alkene, and I'll show you what I mean when we get to that point. The other thing is you need something that's being added that's two different stuff. So, first question here, you see how you're adding hydrogen bromide. So there's two different things that can be attached to that carbon. When this gets added to the alkene, one carbon needs to get a hydrogen, the other carbon needs to get a bromine. So that is not going to, that's two different things being added. If you said, for example, had hydrogen and only hydrogen gas, or bromine and only bromine gas, so H2 or Br2, in both cases, both carbons get the hydrogen or they both get the bromine. So in that case, that doesn't have Markovnikov's rule applied to it. Are we okay with that as a concept? So it needs to be two different things. The other thing is that it needs to be unsymmetrical. So I'll show you what a symmetrical molecule looks like once I go through the answers. So in this case, we are breaking the double bond. And when we break that double bond, now my carbons only have three things attached to it. So I need to attach a hydrogen to one of them and a bromine to the other one. The way I decide that is by counting the number of hydrogens on the carbon involved in the double bond. So this carbon here has 1, 2. This carbon here only has 1. I am not counting these hydrogens because that is not directly involved in the double bond. Now, we have to weigh which one's rich and which one's poor. This one has 2, that one has 1. So we will be using Markovnikov's rule. I will have 2 products, and the major is going to be found in a higher percentage. Thus, you have more of it. So you're more likely to get that product. So that should be C, H, 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 because the rich get richer. The one with the most hydrogen gets the hydrogen. It's very sad, kind of reflection on economics. Br, H, C, H, H, H. That's my major. The minor is the opposite. So let's say by chance someone wins the lottery and the bromine actually goes to carbon 1. And let's say the IRS finally found out about the tax fraud. That's the minor. Are we okay with that so far? All right. What happens if both my carbons have the same number of hydrogens? That's a 50-50 mixture. Okay? So I'll make that as a note. If both carbons have the same number of hydrogens, it's a 50-50. You still get 2 products, they're just in a 50-50 percentage. If carbons have same number of hydrogens, then it's a 50-50 mixture. Okay? Are you good with that? All right. Last thing I want to talk about is symmetrical alkenes. So what do they mean in reference to everybody? I'm just watching my time. So let's say, for example, I have C double bond C, H, H. I'm trying to think. How do I make a symmetrical alkene without... Oh, I know. CH2, 3, CH2, CH3. All right. Yes. No. Hold on. That's the example for the other one. That's not what I want. trying to think of what I would describe as a symmetrical alkene. Maybe symmetrical alkenes do have the same. I'm just going to draw this one because I can't think of anything right now. All right. So in this case, we have a 50-50 mixture, but the thing is we only have one product. Because if I break the double bond and I add my bromine here and I add my hydrogen there, it's on carbon number 1, 2. Agreed? If the opposite occurs, and this guy gets the hydrogen, and this guy gets the bromine, if I count it, it's 1, 2. So do you see how, regardless of what I make, it's still going to be a 2-bromo? So that's what they're referring to when they're talking about symmetrical. Do you want me to backtrack, Julia? Okay. So this is my carbon molecule that I'm breaking. I break, it's symmetrical. So it's reflective of each other. If I remove this double bond and I add the bromine to carbon 2 over here, then it's 1, 2, it's 2-bromo. If, on the other hand, we get the other product and I attach the bromine to carbon number 3, well, actually, it's carbon number 2, 1, 2. So it's still 2-bromo. So that's what they're talking about. So it only works if it's not symmetrical. Are we okay with that? All right, just watching our time, so I want to make sure I get through Zaytev's. So Zaytev's rule is an example of an elimination reaction. So we are removing stuff. All right, so I have an organic molecule here, and we are going to be removing a fluorine from this organic molecule, so that way I can make a double bond. I need to remove something from a neighboring carbon, because when we're talking about alkenes, they're always involved 2 carbons. So if I look, I have the right and I have the left. All right, this one's actually a very poor example because you're going to get the same product either way. So let's do the one on the bottom. All right, this is a better one. So this is, again, a good way to kind of see the difference. So this here is my fluorine. I can either remove the the hydrogen from carbon number 1, which has 1, 2, 3, or I can remove it from carbon number 3, which has 2. Do you see what we're saying? All right, so that means I can have 2 products. In Zaytev's rule, the poor gets poorer. Again, very realistic statement on economics. All right, so this is the rich guy, that's the poor guy. So we're more likely to lose a hydrogen from carbon number 3 and form the double bond here. So that is my major product. No, wait, what are you doing? That's my major product on the bottom. The poor gets poorer. Are we okay with that? All right. However, every so often, people get lucky. Instead, maybe this hydrogen stays and we remove this hydrogen instead. So that then forms the double bond between carbon 1 and 2. So this is my minor product. So basically, Zaytev's rule is just Markovnikov's rule in reverse. You might hear it being referred to as anti-Markovnikov's rule for that reason. Again, just being mindful because these guys do pop up in the flow chart every so often. Oh yeah, identify which is the major minor product. Cool. This can also have possibilities of cis-trans isomers. So this guy here, the minor product, can form cis-trans isomers. This guy, the major, cannot. Because when you look at it, sorry, my bad. Major can have cis-trans isomers, minor cannot. Because the minor has 2 hydrogens. Okay? So when you guys are looking at some of the questions, they might give you hints being like, oh, it cannot form cis-trans isomers. Then you know it's this product. Or sorry, then it cannot form, it's this one. If it can form, then it's this one. Getting my words confused. All right. Questions, concerns, comments. I see some worried faces. Do we need me to go over major, minor for this guy? Okay. Fluorine's over here. Now, when we form a double bond, the carbon can either form it between carbon 1 and 2 or 2 and 3. So we need to look at the neighboring carbons to see how many hydrogens are there. We look at this guy, it has 1, 2, 3, and then if you look on this side, it only has 1, 2. So this guy is the poor carbon. This guy is the rich carbon. So in this case, the poor is more likely to get poorer. So this guy will lose the hydrogen. If this guy loses the hydrogen, the double bond forms between carbon 2 and 3, forming that guy here, 2 and 3. If, however, the rich gets to an awful accident or the IRS finally calls them up and they lose their hydrogen, then the double bond forms between carbon 1 and 2. 1 and 2. All right? Those are the rules. All right, do those practice SciPad pages because they're useful. How many people are going to be here on Friday? And how many people are probably going to be away on Friday? Who's going to not be here on Friday because they're doing their hair and nails? All right, let's go number-wise. Hopefully we have enough people here. When I asked my level 2 class that, a lot of them were like, not going to be here, going to get my hairs done. I was like, yeah, guys, you're learning. Alrighty.